Section 2.4. This is the last section of Chapter 2. Then we move on to Chapter 3, where we do a lot more things with derivatives. So 2.4, rates of change and tangent lines. First of all, we have already had our two formulas for average rate of change and instantaneous rate of change. We're going to come back to those and talk to them about those a little bit before during the rest of the section. So average rate of change is, of course, our change in y over change in x. Our change in y would be our y2 minus y1, or in other words, f of x2 minus f of x1, divided by x2 minus x1, which is also the slope of the line passing through the points x1, comma, f of x1, and x2, comma, f of x2. Okay. Instantaneous rate of change, we are only looking at one point, and so we're saying the slope of some f of x function at just some a, comma, f of a. And is defined as the limit as h goes to 0 of f of a plus h minus f of a all over h. And as I said in the other video, that it is very similar to our average rate of change formula, right? Instead of x and x1, well, x1 and x2, we're looking at a and then a plus h. Really just a slope formula, and then we want h to be as small as possible. So we have a limit as h goes to 0 in the front. And this is also equal to the derivative at a. This is a really important concept that we do in calculus, and we will really get into more depth in the next chapter. But our notation is f prime of a, saying the slope of our f function at a. Right? F of a would be the y value at a. F prime of a is the slope of our f of x function at a. So, moving on, we use the average rate of change to find the slope of a secant line. So, I have my graph. And let's do a cubic function. And the slope of my secant line, let's put 2 points on there. I'm going to do this one and this one, any 2 points. So the line that's connecting 2 points on a graph is called a secant line. So the slope of this line, we would just use our regular slope formula, and we would find the equation. Well, first we would find the slope, and then we would use that in order to find the equation of that line. Perfect. So there's my secant line. It's the line that passes through 2 points. I could have a secant, the other point be somewhere over here, right? It could be anywhere. And then my secant line would look like this. Okay? Secant lines, I'm just taking 2 points, finding the slope that goes between the two, and then find the equation of the line using one of those 2 points. Okay, and we use instantaneous rate of change in order to find the slope of a tangent line. Tangent line is different because we are only looking at one point now. So it doesn't matter what the function's doing near it, but at that point, as long as the function is continuous and differentiable, which we haven't even talked about yet, but as long as there's a derivative that exists, so as long as the slope exists, right, if it's not coming to a point, there's no asymptote, of course, then the function doesn't even exist. We'll get into that later. Then we can draw a tangent line. So say this point right here. Well, what is the function doing? It is increasing. It has a positive slope right here. And I can draw a tangent line that has the same slope as the slope of the function at that point. So it would look something like this. Maybe a little bit over. Okay, so here is my tangent line. Okay, so it's the same, the slope of this line is the same as the slope of this function, even though it's a curve, at that point right here. Okay? Because it's a curved function, the slope is changing all the time, but at that one point, right, the slope of the line is the same as the slope of that tangent line. Okay? Let me just draw another one in case you need more examples to visualize. Let's do one where the slope is negative. And where's my line? So then my tangent line is going to look like approximately like this. It's a little hard to aim on here. Okay, so something like that. And we're going to do examples where we come up with the equations of these lines. I'm just trying to show you visually what it would look like. The normal line, which is new to you, to a curve is the line perpendicular to the tangent line at that point. So perpendicular, right? We're just finding the equation of a perpendicular line, which you know how to do. We just didn't name it as the normal line before. So let's do one example, and then we finish with a section. Let f of x equal x squared plus 3x minus 5. Find the equation of the secant line that passes through f of x at x equals 1 and x equals 4. So our first job is to find the slope between those 2 points. So I have f of 4 minus f of 1. It's our average rate of change formula. In other words, it's our slope formula. Divided by our change in x values, which is 4 minus 1. Let me label that as our slope. F of 4, and plug 4 into my function, I get 16 plus 12 minus 5. Is that what I said? 16 plus 12 minus 5. And that gives me 23. Divided by 3. So that's almost 24. That's 7 2/3. We'll just leave it as 23 over 3. Oops. Did I subtract 1? No, I did not. Okay. F of 1 is 1 plus 3 minus 5 is -1. So minus a -1 is plus 1. Oh, thank goodness. Now it comes out as 24 over 3, which is much easier to work with. I thought I made it a nice example. Okay, so now I need 1 point. I'm going to use the 1 and 1 comma something, because 1s are just usually easier to work with than 4s. I need to figure out my y value at 1. Well, I just did it, and it is 1. Okay, so now I have the point 1 comma 1, and I have a slope of 8, so I can find the equation of the line. And I just plug it into my point slope. Y minus 1 equals 8 times x minus 1. Of course, I could have used either of these points here, right? I could do the point at 4 comma 23, and it would have been the exact same line. Okay. And it doesn't tell me how to write it, so I am going to leave it like that. Okay, next one says, find the equation of the line tangent to the function at x equals 1. Okay. So in order to find the equation of the tangent line, I need the slope at any point. Well, I can't find the slope at 1 and using just 1 and 1, because then I would get 0 over 0, right? If I had f of 1 minus f of 1 divided by 1 minus 1, 0 over 0, I need to do something different, okay? And my something different is this limit formula, okay? So this is how we find derivatives, right? That is our f prime of a. So I could go ahead and do the whole limit formula, but we've done that all last year, right? Now, and then we learned the shortcut that we can find the derivative much, much quicker. Remember the shortcut, f prime of x. Shortcut says I take the coefficient, so my coefficient here is 1, times the exponent. 1 times 2 is 2. X to the, and I decrease this exponent by 1. 2 minus 1 is just 1, so I get 2x. Plus, and do the same thing for all these terms. You don't know how to do it yet when you don't have a polynomial? Don't worry, that's what calculus is for. So I have 3 times 1, okay, and then x to the 0, so it's really just 3, right? 3 times x to the 0 is 1, so it's just 3. Also think about this as being a linear function, because it is, right? Just the 3x term. And the slope of that function is always 3. The slope of x squared is always 2x, right? The slope at every point on an x squared function is twice whatever the x value is, okay? And the slope of -5 all the time is a horizontal line, and therefore the slope is 0. Okay. So the derivative of my original function is 2x plus 3, which tells me what my slope is. My computer just dinged, I don't know why. It tells me what my slope is at any point x. So I will plug in x equals 1. So I have f prime of 1 equals 2 times 1. I just plug 1 into that function that I just found. plus 3 equals 5. So the slope of this function at 1 is 5. Okay. Well, luckily, I already found the y value at 1. Still the point 1 comma 1. Now I just need to write the equation of the line that has a slope of 5 and passes through the point 1, 1. So it's just y minus 1 equals 5 times x minus 1. And it is that easy. I'm only going to give you polynomials for now because I haven't taught you how to take derivatives of anything else yet. Being a little bit better at writing with this mouse. And the last one, find the equation of the line normal to f of x at x equals 1. Normal, of course, meaning perpendicular. So if the slope, we already found our slope function, okay, and then we plugged in 1 and we found that the equation, that the tangent line has a slope of 5, meaning that the line perpendicular to it has a slope of the opposite reciprocal of 5, which is negative 1 over 5. This is an even easier question because I already had this slope right here. So now I'm just plugging in once again, because it's at x equals 1 again, y minus 1 equals negative 1/5 times x minus 1. And that may be my shortest video so far. You have a few homework questions? Not many. And I hope this all made sense. See you tomorrow.